Good morning, everyone. Today we're going to basically wrap up our topics from Chapter 10. And just as a recap, all of these problem sets in Chapter 10 can sometimes seem disconnected. They're basically preparing us for future courses, but there is a trigonometry component to most of them. Up to this point, we've looked at polar coordinates and how to convert between rectangular and polar coordinates. We've looked at polar graphs, the rows, the cardioid, and when working with those types of classic curves, it's very important that you use the calculator and that you know how to change into polar mode and get the theta right, get the step right, so you can see what you're supposed to see and kind of identify them once you see the picture. Lately, we've been working with vectors. We know that vectors are basically some type of something with a quantity, a measurement, a magnitude, and a direction. Can be used to solve a variety of kind of physics-type movement problems. But we can also just think of vectors kind of as a set of ordered pairs. And we can add them, we can subtract them, and so forth, even multiply them by a scalar number and put them together in different ways, geometrically or algebraically. The one piece we did skip, because with this change this year, we've been told not to worry about it, is de Moivre's theorem. And it's kind of good that we don't have to deal with it because it can be rather challenging, but at the same time it's kind of neat because it makes some connections between some of these other types of things. So just wanted a recap of where we're at so far. Now with vectors, we know that we can add vectors, subtract vectors, and again multiply by a scalar, which means if I take 2 times a vector, it just doubles the length, you might call it. But one thing we haven't done yet is to multiply vectors. And what does it even mean to multiply vectors? Well, it turns out with vectors, there are 2 different ways of multiplying them. One is called a dot product, and sometimes one is called a cross product. We're going to be concerned with something called the dot product. Now, a more formal name for it is scalar product. The reason is the dot product, or scalar product, once we calculate it, is just a number. If we were to look at the cross product of 2 vectors is another vector. But that's something we're not required to look at. With the dot product, it's pretty much a kind of a rather simple calculation. And let's just start with 2 vectors. If I have vector A or V, and it's like AI plus BJ, and then vector U is, let's have subscripts here. We have another coefficient of I plus another coefficient of J. U or V dot U is basically the sum of products. It's going to be the 2 coefficients of I multiplied together, so A1, A2 plus the 2 coefficients of B multiplied, or J multiplied together. And that's going to give us a number. You can maybe see why we call it a dot product, is because there's a big dot in between. It's as simple as that. For example, I could give you these 2 vectors. Let's say vector V is going to be 2I plus 3J, and vector U is going to be 4I minus 2J. And therefore, the dot product, V dot U, is simply 2 times 4, which is 8, and that's negative 6. So you get a dot product of 2. So that's all well and good. That's what the dot product is, but what in the world does it mean? It seems like a made-up random calculation. Well, this is what it really means to us. Let's take a closer look at these as far as a graph. If I were to take 2I plus 3j, I can think of that as 2, 3. So it's kind of this vector. Okay, that's 2I plus 3j. Well, this other vector, 4 and negative 2, would be moving out 4 units and down 2. So we can think of it as this vector. Okay, so we have the dot product. That's 2. Well, one thing about the dot product is it is going to tell us whether or not the two vectors are perpendicular. All right, and if they're perpendicular, the dot product is 0. That means the vectors are perpendicular. And it's a two-way street. Now, another word we have for perpendicular is orthogonal. Anytime you see a word with ortho in it, it has something to do with right. Orthodontist makes your teeth right, okay, or right angles. So if you're asked to decide if two vectors are orthogonal, you simply find their dot product. If it's 0, they're orthogonal. If not, then they're not orthogonal. They're not perpendicular. Now, here's what else it can mean. Let's say it's not 0. Well, then we can find the angle between two vectors. Now, as far as the angle between two vectors, the cosine of that angle is going to be the dot product of the two vectors divided by the product of the magnitudes. And that's not a dot product, that's just a product. Now, the derivation for this is basically going to be a cosine rule. And we could get to the derivation, but I'd really rather not spend time with it at this point. So let's look at another example. Let's find the angle between, let's say U is 4i minus 3j, and V is going to be 2i plus 5j. Now remember, we could just think of these vectors kind of as ordered pairs with these squared off parentheses. And eventually we're going to maybe drop this ij notation because it can get a little cumbersome. But either way, these are the two vectors. So in order to find the angle between the two, maybe I'm first going to sketch them just to get a feel. 4, -3 would be kind of this one. That would be U. This would be 2, 5 over 2 and up 5. It'd be this one. They don't seem to be perpendicular. So what I'm going to do is find the dot product. U dot V would be the product of these two, which is 8, plus the product of these two, which is -15. So I get -7. The magnitude of U, that's basically the Pythagorean theorem, square root of this squared plus that squared is going to be 5. The magnitude of V is going to be radical 29. So to find the angle, I'm basically going to have this 7 over 5 times radical 29. And with some calculations, I believe we get it to be about 10 degrees, but I'll let you go ahead and finish that. And by the way, we typically want this to be a positive number, so many times we would take the absolute value, because if we think about the angle between these two, you know, if we got these directions, there could be a couple. We want this theta, right? But again, graphing it can give you some reason to kind of suspect whether or not it makes some sense. So, long story short, in multiplying vectors, there are a couple ways to go about it. Probably the most useful for our purposes is going to be dealing with something known as the dot product. The dot product is simply the sum of a product of the kind of components, the I component and the J component. If that dot product happens to be 0, we know the two vectors are perpendicular. If that dot product is not 0, we're not done. We can then go ahead and find the angle between two vectors using this formula. This, of course, are the magnitudes. This involves the dot product. We then have to use inverse cosine. So again, it's a little bit of trig, but not very much. That's the basics of the dot product. So if you have any questions, please don't hesitate to contact me. And I know there are some problems in the problem set that involve work and force. They're mainly physics problems. But I think if you study the examples, you might be able to get through them. If not, please let me know, and I can maybe set up a quick little video with some of those types of examples. Have a good day, and we'll see you soon.